Today we're going to be talking about waves some more, but this week we're going to be focusing on light and color. So I'm going to start off with just a little bit of a review about waves in general. So remember that waves carry energy, okay? Waves carry energy. Last week we were focusing on general information about waves, and we spent just a little bit of time talking about sound. And this week we're going to be focusing on light, okay? So regardless of what type of wave we have, the answer is always energy as far as what a wave carries. Now, we talked about two categories of waves. We have mechanical waves, which are waves that require some sort of particle, medium, material, atom that can be vibrated or oscillated as it carries that energy through the space or through that material. This week, we're going to be focusing on electromagnetic waves. So electromagnetic waves, if you do not recall, these are waves that do not require a medium. So these are waves that can take place and the energy can be carried even if there are absolutely no atoms in that space. Okay, so our examples here are light and radio waves. And it says all waves on the electromagnetic spectrum are going to be waves that do not require any type of medium or particles. We discussed wave speed briefly last week. And so basically what we learned last week about the speed of a wave is that the speed of the wave can be calculated by multiplying frequency times wavelength. We also learned that the speed depends on the material that the wave is passing through. So for any given wave, the frequency and wavelength is going to give me the wave speed, but then how fast that wave physically travels from point A to point B, that is going to be influenced as well by the medium. And so we'll talk about the math that goes with this chapter in another lesson. And so we'll get into some more details about that and how to actually carry out the math work for that. But for now, just remember that wave speed depends on the medium that the wave is traveling in. Now, for all electromagnetic waves, that speed is going to be 3 times 10 to the 8th meters per second in a vacuum. So what is a vacuum? A vacuum is an area where we have absolutely no particles, okay? So this is an area or some sort of containment space that is void of atoms, void of particles. So when we are talking about the speed of a wave, or when we're talking about specifically light speed, we're going to be talking about the speed if that light wave were passing through an area where there were absolutely no particles. So a vacuum is the word that we often use for that. All right, so let's talk briefly about the electromagnetic spectrum. The electromagnetic spectrum is a range of different types of waves that are all classified as electromagnetic waves because they do not require atoms in order to create that wave. So what you see at the top of the slide here is an illustration of a wave. For my visual learners, I love this picture because I know for me personally, this helps me to understand what is happening to the wave as we move across the spectrum. And it also helps me to have some sort of visual reference whenever I'm being asked questions about our wavelength or frequency or the energy of the different types of waves on the spectrum. So you can see from the illustration that the waves start off far apart from each other, and then as we move across the spectrum to the right, those waves get closer together. So we'll talk about what that means in our vocabulary terms here in just a second. Okay, some general information about electromagnetic waves. They carry radiant energy, and they can travel either through matter or through a vacuum. So I know I said electromagnetic waves do not require a matter, but they can actually travel through a medium. So for example, visible light that you and I can see with our eyes. I am currently sitting in a room with the light on. I know that there's air in the room with me because I'm breathing. So that's a matter, or that is matter. That is a medium. Those are particles, and the light is still passing from the light bulb at the top of my room to my eyes. Okay, so it can travel through a medium, but it does not require a medium. So how do I know that? Well, a vacuum would be a space where there is no matter, right? There are no particles. So let's think real life, naturally speaking, where would such an environment exist? Well, in outer space. So how do we know that light indeed can travel through outer space, through an area where there are no particles? Well, guys, we get light from the sun. And the sun is far away in our solar system, right? It's far away from us. So that means that the light must be able to travel all the way from the sun through outer space where there are no particles and then make it to Earth's atmosphere where there are particles and then to our eyes, right? So just looking at sunlight, we can see that it can travel both with or without particles being present, but it does not require those particles. All right, so what are the different types of waves on this spectrum? We have radio waves, microwaves, infrared light, visible light, ultraviolet light, X-rays, and gamma rays. Now, I do want you to be familiar with what the different types of waves are on the spectrum. You may be asked a question or two about these waves as far as, or these types of rays as far as how they compare to each other. So I would maybe see if you can try to remember what they are in order. I do want you to understand in general that radio waves are the farthest to the left. So if we look at our illustration, the illustration shows that the waves the farthest to the left are the farthest apart. So what does that mean using our vocabulary? That means that radio waves, out of all of these waves on the spectrum, are going to have the longest wavelength. And so as a result of that, that means it's going to have the lowest frequency. Remember, frequency is how often the wave occurs. So the farther apart the waves are, the fewer of them that are going to occur within that 1 second of time. And then I also want you to know that frequency and energy are going to follow the same pattern. I always tell people, pretend that these waves are kids. The more energy they have, the more frequently they're going to move. So your fidgety kids usually have lots of energy, right? As we move across the spectrum, those waves get shorter and shorter. So by the time we make it all the way to the far right side where the gamma rays are, these are the shortest wavelengths. Therefore, they have the highest frequency and the highest amount of energy. Now, right in the middle of the spectrum is visible light. This is the only type of electromagnetic wave that we can actually physically see with our eyes. This is going to cover all of the colors of the rainbow, and we'll talk about them in more detail here in just a bit. Okay, so make sure you understand visible light is in the middle of the spectrum, and it's going to include the different colors that we see. All right, now let's talk about some wave behaviors. This is kind of the Cliff Notes, a brief overview of the 3 types of behaviors you will be expected to know. You might get an illustration demonstrating these vocabulary words. You might get some sort of description of an example of something that's happening to a wave, and you'll need to tell me which of these behaviors it is, and it might just be a definition type of question, okay? So these are not official definitions. This is just kind of a quick little keys to remember that might be helpful for you. So diffraction, we're going to be talking about waves passing through holes or around a corner or an edge. Reflection, waves are going to be bouncing off of some sort of surface or boundary. And refraction, the waves are going to be passing through some sort of material. Okay, so wave diffraction. It says that we have waves that are going to have some sort of change to the direction that it is traveling, and as a result of this change in direction, it changes the shape of the wave. So you can look at the illustrations here. The example says that this allows you to hear things around the corner or through a cracked door if we're talking about light. There might be a night light on in the bathroom, but yet it is able to spread out and kind of light up the hallway so that if the kid needs to get up in the middle of the night to go to the bathroom, they can see well enough, even though it's just a small light coming from a small opening. through that bathroom door, right? So basically, diffraction causes the wave to fan out after it has either passed through the hole or around a corner or an edge. And so this is diffraction. Reflection, I hope we are all pretty familiar with. The general idea is that the wave is going to travel and it's going to bounce off. Some specifics that you might not have thought about is that the wavelength that comes off of that boundary is identical to the original, right? So here it says it has the same wavelength and the same frequency as that original wave. So if we're talking about sound, an echo would be an example of a reflection of sound where you hear your own voice. In an echo, you sound exactly the same because the wavelength and frequency of the voice you created is the same wavelength and frequency of the sound that made it back to your ears. If we're talking about light, seeing yourself in a mirror, provided that this is not a trick mirror. What you see when you look at your reflection is what everybody else sees when they look at your face directly. The wavelength and the frequency are identical to the original, okay? Now here I have an illustration. You will be asked some specifics about reflection that maybe you don't just instinctively know. All right, so let's make sure that we address these really quickly. Over here on the left, it says the law of reflection says that when a ray of light reflects off of a surface, the angle of incidence is equal to the angle of reflection. Now that's some science vocabulary there. Don't get overwhelmed. Look at the illustration. Whatever angle the beam of light went into the boundary, it bounces off with the same angle, right? It's the same tilt of the light, same degrees if we're measuring in degrees, but notice where the measurement is coming from. The measurement is not coming from the boundary itself. The measurement is coming from this dotted line that just kind of magically appears. Well, that dotted line has a name. So if you look at the illustration, that is your normal line. Now, this is not a physical line that we see in real life. This is a reference point. And if you notice, this dotted normal line is popping up perpendicular to that reflective surface. So the normal line is always going to be perpendicular to the reflective surface, and that's where the measurement is coming from, okay? So I have this kind of still image so that you can see a little bit easier what is being measured. So notice the angle of incidence, which starts with the word in. The angle in is the angle of incidence, and that is the same as the angle out, or the reflected angle, and it's always measured from the normal line. So just be prepared to have a question or two about this concept, okay? All right, the last type of wave behavior is called refraction. And so here it says that the wave is going to bend when it crosses a boundary into a material of a different density. The key here, guys, is that it passes into a new material. That is the key to identifying refraction with an R. Okay, refraction and reflection sound similar, so make sure you read carefully and that you pay attention to which type we are referring to. So refraction with an R, we have light that's going to pass into a new material. Well, that material is made of some sort of combination and arrangement of particles, which creates the density of that material. So if we say that the wave is either going to be passing through the particles if it's mechanical, or it's going to be passing in the space around the particles if it is electromagnetic, then the arrangement of those particles is going to determine how easily or not the light or the wave passes through that material. So as the wave makes the adjustment of being able to pass through easily or having some difficulty passing through, that essentially affects the speed at which it physically gets from point A to point B. And so in this particular case, that change in speed is going to change the path that it is on, okay? So we say that the wave bends, but really what happens is that the speed changes, and so that change in speed changes the outcome of the path that the wave is on, or where that wave ends up, compared to if it had traveled without changing into a new material. All right, so down here we have a specific example of refraction. And guys, I want you to remember this. You need to know that a mirage is an example of refraction. A mirage is an example of refraction. Okay, now we often discuss this in the classroom, and I ask kids questions, and there's a lot of kids that easily get confused and they want to say that it is reflection. No, it is refraction. So here's what happens in a mirage. You have light that bends because on a super hot day, the density of the air right at the surface of the road is it has changed, because with the heat it changes the density. Hopefully we remember that from chemistry. So instead of the light passing through those air molecules and landing somewhere on the ground where you don't see it, instead the light passes through, and because of the change in density, it causes that light wave to bend so much that the light actually ends up coming up. And so our eyes receive blue from the sky to our eyeball, but it's coming from the ground. So it looks to our brain like water, because that's what we're used to seeing when we see blue light on the ground, but it's not really water. If you've ever been on the highway in Texas in the middle of the summer, you see what looks like little puddles, right? But guys, July, August, there's no rain in Texas. There's no water on the ground, right? So this is refracted light, light that has been bent because it went into the air of a different density, which changed the speed of the wave, which changed the path that the light wave was on, and changes the location of where it comes out of that material. And so that is what we call a mirage. Okay. All right. So you will be expected to understand the difference between refraction and reflection. So reflection, basically we hit a boundary, we come in and we bounce back. So our boundary here is air and water. So this right here is our separation between our two materials. So reflection, we stay on the same side, we stay within the same material, it just bounces back. With refraction, now we have a light ray or a wave of some sort. We're going to talk about light specifically, that comes into this boundary, but now it passes through. And as it passes through, because the new material has a new density, it changes the speed with which the light passes through that material, which changes the location of where the light ends up. Okay, now you guys are not going to be asked too many super specific questions off of this just because of our home learning situation. However, I do want to just briefly explain to you, because you guys know I feel very strongly that it's super helpful if you understand, because then you can interpret the questions, okay? So if we were to follow this original beam of light, and we were to say if this light was undisturbed, it would travel, if I can draw this straight, and this is where it would have been if it was not disrupted, right? This would have been the original path that it would have traveled in. But since it entered into a new material, since this beam of light came in, and then once it crosses this boundary, it's now in water. Water has a different density. Water is more dense than air. So this is going to slow down our light wave. Okay, so we're talking specifically about light right now. So light is going to travel in the space around the particles, and so that means the more dense it is, it kind of has to maneuver its way through the empty space, and so that's going to make it more challenging to pass through denser materials, and that's going to cause it to slow down. So as a result, instead of ending up over here, it follows this path. So you can see that it is now closer to this normal line, this imaginary reference point that is perpendicular to our boundary. It is now closer to the normal line because it has entered a more dense material. You will be expected to answer questions about whether the light is closer to the normal line or farther away, and how we word that will change a little. So we would say, for example, on this particular picture, that this angle is smaller than what it would have been if it were undisturbed, right? So this is a smaller angle. We would say that it has moved so that it is now bending towards that normal line because it is closer to the normal line. And we would say that, well, I guess that's the other way we would say it, that it's closer to the normal line. Okay, so be prepared to answer questions like that. You can go to my Google site. So if you've forgotten how to get there, you can always just go to Google and type in Miss Espinosa Physics. And there are some really helpful videos. The top 4. So there's 2 columns of videos. The top 2 on the left are going to be talking about light behaviors. The top 2 on the right are going to be talking about color. So if you feel like you need some more information, go check out those videos on my Google site. Okay? All right, so let's talk a little bit more about light specifically. Light is a transverse wave that we can see. Now, you should already know that this is a form of energy. If you've ever changed a light bulb, you know that light gives off heat. It has color. We've already talked a little bit about the different colors in the visible light spectrum, and it can follow these different wave behaviors that we have discussed. The speed of light, remember that light does not require a medium because it falls under the electromagnetic wave spectrum. It's going to travel fastest in less dense material. So what is the absolute smallest density? If we are saying that we want to travel in the space around the particles, well, guys, if we had no particles, that would be the absolute fastest that it could travel. So light traveling through outer space or light traveling through a vacuum is the absolute fastest. So what we would call the true speed of light, aka light speed, okay? If it is traveling through some sort of material or medium, then the fastest that it will travel is through air, because the density of air is so low that it allows the light to travel actually close to its true speed. Make sure that you understand that concept of what type of materials affect the light, or how the material affects the light speed. So the speed of light, as I mentioned before, is 3 times 10 to the 8th meters per second. This is going to be the value C, which is a constant for us. And again, we'll focus on the math in a different lesson, but I want to make sure that you know that all electromagnetic waves are going to pass through, are going to have a value of 3 times 10 to the 8th for that speed. Okay? All right. Polarization. I don't know if you've heard of polarized sunglasses or any type of polarizing filter on a camera lens, but a polarizer is basically a special type of material that's going to filter out light, okay? You are going to be expected to understand in general what a polarizer does. So it says that light oscillates in multiple directions. It's kind of difficult to illustrate sometimes because, you know, on paper I can only draw so many dimensions, but in real life, light is super high energy, and so it's oscillating or bouncing around, and as a result of that, it kind of flip-flops as far as which axis it moves on. So when we're talking about a polarizer, this is a material that's going to allow some of the light through and block everything else. So we have some illustrations here. You can see at the top of this picture, we have arrows pointing in all different directions. Again, try to understand what this would look like in 3 dimensions. And then we have the polarizing filter, and then after the filter, only that one direction or one axis of light was allowed to pass through. And that's basically what all these different illustrations are showing you. Feel free to go pull up the PowerPoint and take some more time to study these pictures. This illustration over here on the right is showing you what would happen if we have one polarizing filter. It allows what we would say is 50% of the light. So here, if you look at the illustration, these polarizing filters are vertical. So only vertical light would be allowed to pass through, and we would say that that's 50% of the light that made it through the filter. If I have a horizontal filter, then my filter allows horizontal light to pass through, right? So that would be 50% of the light. So if in this picture, we are combining vertical light here and vertical polarizer here and horizontal polarizer there. Well, if you look at it, one allows vertical, the other allows horizontal, but when you combine them, they block both types, right? Because if it allows vertical light through, then that means everything else gets blocked. So when we are talking about polarizers, the direction of the filter is the direction of the light that passes through, and everything else gets blocked. So in this particular question or illustration, if I take vertical and horizontal and I overlap them, I mean, guys, take your hands and turn your fingers so that one hand is pointing vertically and the other is pointing horizontally, and overlap them. You basically make a grid where you would block everything, right? And so that's what this illustration down here at the bottom is showing you. This is a demo I would typically do in class, but you can see as the teacher holds the polarizers so that they are perpendicular to each other, meaning we've got vertical and we've got horizontal, so when you combine them, they overlap and block everything, right? So 0% of the light gets through. Make sure you understand this concept right here, because that will be asked of you in the future. All right, the last thing that we need to talk about today are colors. So again, colors are part of the visible light spectrum. So whenever we're talking about colors, I want you to remember that this is part of the EM spectrum. These are electromagnetic waves, but we're focused specifically on visible light. Remember, that's located in the middle of the spectrum. And then I went ahead and copied the illustration of the waves down here, because that wave, this wave illustration that I gave you on that opening slide, is there to give you a visual understanding of what happens all the way across the spectrum. So when we're asking you questions or making comments about the different colors and their wavelengths and frequency, they follow this same pattern, okay? So Roy G. Biv, if you've not learned that acronym, you probably want to take time to learn it. This is basically the different colors in order, starting with red on the far left-hand side. So that means the left side is going to be the longest wavelength and the shortest frequency, or lowest frequency, however you choose to say that. So red, orange, yellow, green, blue, indigo, violet. So on the far right-hand side, this is going to be where we have the shortest wavelengths or the highest frequency for the color violet. Okay, so when we're talking about colors, we can talk in terms of light and we can talk in terms of pigment. So when we're talking about light, the primary colors of light are red, green, and blue. You need to know this. You need to know this. The primary colors of light are red, green, and blue. If I were to take all three colors of light and mix them together, combine them, overlap them, take a green bulb, a red bulb, and a blue bulb for a flashlight and shine them all in the same spot, I'm going to get white. So white is the presence of all colors, or the combination of all colors. If I turn off all the lights, cover my eyes, have absolutely no light, if you've ever been in a deep, deep, dark cave, that's what we refer to as black. Okay, now this part of the conversation can get a little trippy. I will try to keep it simple for you. All colors mixed together makes white. Combine all the colors together, when we're talking light, you make white. Close your eyes, turn off the lights, you see nothing, that's what we refer to as black. So black is the absence of all light. When we combine light to make new colors, we call this the additive process, because we're adding wavelength of light, frequencies of light together to be received by our brain, and our brain takes the different signals and puts them together to determine what color we're seeing. So the additive process, it says, occurs because new colors are formed by the addition of more than one color signal. So remember that our primary colors for light are red, green, and blue. So what happens is when our brain receives a signal for the different types of colors. So each color has its own wavelength and frequency, and so those wavelengths and frequencies are detected by the nerves in our eye, and then that signal is then transferred to our brain, and our brain interprets what it is that we see. So this is why we call it the additive process, because our brain is adding these three colors. Now our eyes are capable of detecting red, green, and blue. So these are the colors of light that we will speak in terms of to make all other colors, because this is what our brain recognizes. Once again, check out some of those extra videos on my Google site if you feel you need some more explanation. I just have a quick little color wheel here to show you what we're going to combine to make what. You will be asked questions about this, so please on your own take time to study this color wheel. Red, green, and blue are our primary colors, and you can see from the illustration where the green and the blue mix together, we make what we call cyan. Where the red and the blue mix together, that is called magenta. Where the red and the green mix together, that is called yellow. Okay, so you're going to be asked questions about if I combine red light and green light, that makes, and then you need to answer yellow. And then you can see right here in the middle where all three colors mix together, that makes white light. So what gives objects their color? Well, we're going to see objects based off of the color of light that is reflected. So if we have white light that shines down onto an object, white light is going to have all the different colors of the rainbow for us. Some of those colors are going to be absorbed by the fabric, and then the remaining colors are going to be reflected. So what determines the color that we see is the color of light that is reflected. Why? Because we can only see the light that reaches our eyes. That sounds really simple when I say that, but sometimes when we're answering questions, we forget that it's really just that simple. So try to say that to yourself whenever you're answering color questions. We only see the light that reaches our eye. So if I'm seeing something that is yellow, doesn't matter what colors are shown onto it, because white light has all the different colors. If I see yellow, it's because yellow is the only color that makes it to my eye. Okay, so going back to this color wheel, if I see cyan, that means blue. Let's pick a different color here. If I see cyan, that means blue and green made it to my eye, because blue plus green equals cyan. Okay, you'll be asked some questions about how to make colors by combining light. All right, so what's the opposite of combining light to make colors? Combining pigments to remove colors that we don't want to see, and whatever's left over is what we do see. So pigments are when we're talking about dyes, okay? Things that are going to absorb light in order to create the color that we see. So I want you to think of a colored printer. Maybe you don't have a color printer at home. Maybe you've never changed out the ink in a color printer, but color printers do not print using red, green, and blue ink. Color printers print using cyan, magenta, and yellow ink. So how does that work? Well, the dyes and the pigments are going to subtract out colors by absorbing colors. Whatever colors are not absorbed are then going to be reflected. And remember, you see what reaches your eye. So what is reflected determines what color you actually see. So when we're talking about pigments, the primary colors for pigment are cyan, magenta, and yellow. So make sure you know that. Cyan, magenta, and yellow are the primary colors of pigment. So for the subtractive process, we're going to be working backwards, okay? The color cyan, as I showed you on the previous slide here, the color cyan is because blue and green made it to your eye. So in order for me to see the color cyan, blue and green had to make it to my eye. Well, let's think backwards. If my color printer uses cyan ink, that means that it used blue and green, and those colors were put down onto the paper. And we were able to, those colors were put onto the paper, but then they were reflected to our eyes because we were able to see them, right? So in order for me to see cyan, blue needed to make it to my eyeball, green needed to make it to my eyeball. But remember, the three colors that our eyes can recognize are red, green, and blue. So that means red was absorbed by the fabric, by the material, by the paper, and did not make it to my eye. Again, please visit my Google site and check out those extra tutorial videos there, okay? Here is a color wheel for pigments. So once again, you can see the primary colors here are the largest circles. So cyan, magenta, and yellow are the primary colors for pigment. Combining colors is going to cause the colors to be absorbed, and whatever is left over is what is reflected to our eye, and that is the color that we see. And then you can see here, if you combine all three colors, cyan, magenta, and yellow, they are going to cause the fabric to absorb all of the colors. Remember, turn off the lights, cover your eyes. The absence of all color is what we refer to as black. So in the middle of this color wheel, black is what you get when you combine all colors. All right, please take some time to pull up the PowerPoint and study these images on your own. Please make sure that you reach out to me if you have any additional questions, and I would strongly encourage you to do your best to jump on the live session so that you can get clarification on any of these things you may still be confused about. All right, you guys have a wonderful day. Goodbye.